Good afternoon. We will start today on a new topic, intact. Okay, or I can also call this lecture as okay. See, by the word intact stability, basically I am trying to say that we will be studying the stability of the hull under intact condition, no damages. Initial stability would be a part of it in the sense that we will try to figure out the stability under its initial equilibrium condition. Now, before we can go on, we have to first define what is basically meant by the word stability. See, this requires some kind of a discussion. The reason is like this. Now, if you look at the dictionary, you will find large number of meaning connected to this word stability. We in fact even talk things like he is mentally unstable and things like that. Okay, so stability has a very large connotation. Depending on who you are speaking to, stability might mean something. Now, in general, I want to first start giving a general definition. We will tell that stability of a system, let me first write it down. Will be defined by the way a system uh, operates or behaves under an influence of external force given to it and then removed it. In other words, we will say stability of a system is the see. So what I wrote down here is the stability of a system would be defined as how the system would behave if I have given an external disturbance and then I removed it. Why it is important comes like this. See, uh, suppose I have a system there. uh, I'll come to this next slide. Let us say there is a ball here. Okay, now this one can consider this to be a system. It is placed at this is a kind of a hill. Now supposing you disturb the ball, you removed it here. That is a disturbance from its state of equilibrium. You are basically pushing it out from where it was. Then leave your hand. What happens? There are three things that can happen. The ball can stay where it is, it can come back to its original place, or it can actually go farther away from its position. For example, if the ball was here, if you shift it, what would happen? That it is definitely going to fall or go somewhere else. If it is here, for example, if you actually shift it, then what would happen? It will stay wherever you have shifted. See, I shift it, it stays here. This I shift it here, but it comes back. This I shift it somewhere, then it simply goes away. Okay, so these three things tells me that the ball behaves in three different ways. Okay, now this is what is the concept of stability, which basically means that the ball was here as it is. Now I try to move it from its state of equilibrium by giving some kind of external disturbance from outside, somebody has pushed it, there then that push has been withdrawn, has been removed. We pushed it by a, say, hand, and then I removed my hand. Now I want to know how would that system behave. Will it come back to its original state of equilibrium? Will it stay in the disturbed state of equilibrium, or will it deviate further from the disturbed state of equilibrium? So there are three ways it can behave, and this three would actually represent its what is called stability property. Now you can let us consider another example. Say ship is moving. It's our relevant case. The ship is supposed to move on a straight line under a propeller. Now suppose at some point there is some disturbance here. So the ship trajectory has taken some line, something like that. Now I left my hand or left that disturbance. Will it come back here, or will it continue to go like this, or will it be, take a different attitude? This is also stability. We will call that in a different context in later on a dynamic stability. So basically stability is a very wide word. It may has many meanings. So I am trying to say, since we have termed the lecture as stability, we have first have to know which stability I am talking about, because depending on who you talk to, he will understand something else. Now what we here talked is, we will see this term intact. Some people call this hydrostatic stability. Why hydrostatic? Because now that I have my ship here, water is calm, so the only pressure that acts is hydrostatic pressure. It is not moving, there are no waves, the ship is not moving, everything calm and steady. So the only pressure that is acting is hydrostatic pressure. Under this condition, the ship is under an equilibrium position. Now if I disturb it, the behavior of the ship or the vessel would be either it can stay there, or it can capsize, or it can come back. This study, that is under the action of hydrostatic pressure only, how a ship would behave when disturbed from its state of equilibrium, is the subject of hydrostatic stability. That's why we use the word hydrostatic stability. See, one can also say dynamic stability, but what we will study is hydrostatic stability. And there is a very good reason I normally tell in the class: if you cannot make a ship stable when there are no waves, no winds, etc., then there is no point of talking what would happen if there are waves and winds. You see, the first thing is that I must make sure the ship stays in its position as I want it to be in a calm water. So therefore it is very important, because if you cannot steady the ship, you cannot really talk further. There are many ways one can give an example of stability. One more example that is very easy to see, that if I keep this thing here, or some kind of a pen here, you will find that it is very difficult to balance. Technically speaking, there is an equilibrium, the reaction and forces are in one line, but what happens, slight disturbance will always cause it to go down. So again, the system is not stable in this. This is another example of stability of of a system. So as I said, what we want to talk about in our subject in these lectures are ship stability only under the action of hydrostatic pressure. Now it turns out that if you look at a ship here, we talked earlier lectures about its rotation about the longitudinal axis. That means I have rotated about this y axis. Turns out that if you rotate about y axis, the restoring moment, the moment that tries to bring it back, is so large that the ship can never ever capsize in that mode because of its length. Therefore, we never talk about stability in that plane. On the other hand, if you incline it about this x axis, there are chances that it may incline. First of all, in y axis, you can only incline the ship by 2-3 degrees. Okay, but about x axis, you can incline even up to 30-40 degrees. That is why in ship hydrostatic stability, we always talk of stability about a longitudinal axis for rotation in the transverse plane. In other words, we have this cross section and we will talk about its rotating. in the transverse plane. Okay, that is a area that we talked in ship hydrostatic stability, intact stability. I am saying this because in offshore structures sometime when you talk of stability, you may tend to talk about inclination or rotation about both axes, because there it is equally important sometimes. But here we will be talking about only rotation about, this is the long axis, about this x axis. The rotation is this direction. So this is kind of a completes my definition part of what is stability. Now everybody knows about this part. This is rather elementary, that if I take a ship, it's difficult to draw. There is a weight force acting through this, through center of gravity, and there is a buoyancy force acting through this. Okay, when the ship is, now supposing I incline the ship, this is my underwater volume is going to be, well, let me draw it this way. This is underwater. We need another color. Say I incline the ship in this fashion. This is my underwater volume. Now center of gravity, of course, weight still remains somewhere here. It acts like this. Okay. But center of buoyancy is centroid of this area, which would have gone somewhere here. Let us see. So this is my B, this is my G. So through that I have this. This is W. This is buoyancy equal to W. Now you see there is now weight acting this thing, buoyancy acting this side, and this is trying to get me a moment like this. That means basically the ship would experience a moment trying to bring it back to its original position. It will try to restore it back to its position. This is why we can call this to be a restoring moment. On the other hand, now let me say that the same diagram if I draw, but slightly different. These diagrams are not, of course, very. So G is here, and the center of buoyancy has shifted to some position like here, just here. So it goes like this. This is my weight, this is my buoyancy now. So you can see here that this is going to give me a basically moment like this. And obviously what would happen, that it will try to actually cause this to increase the disturbance from equilibrium. So this becomes a case where the ship, when disturbed and the disturbance removed, see this angle was an external disturbance. Somebody has caused a wind or some wave would have caused it to tilt it to some angle. That's an external influence. Then you have left your that disturbance. Question that we want to examine is, should it come back to its original? All right. So here we see that in this scenario it is coming back. In this scenario it is actually increasing, and the third situation that is most rare, most never happens, is that if the G is here and B is exactly below that. So in that case what would happen? It will stay where it is. See the center of buoyancy and center of G remains on the same line. That is very unlikely, because you see if you tilt it slight more, the buoyancy will go either this way or that way. So this is a situation where if it was possible, the ship would have stayed at this location. But in ship study it turns out that you can only have either this or this. You can rarely have this, for the simple reason that if you tilt it even slightly, it will be either becoming this or becoming this. So we normally, nobody talks about situation of a situation where it will remain as it is. This is, of course, you can make out, this scenario would represent a positive stability. In other words, we can say that the ship is stable because it comes back to its original. this is a configuration, we call it unstable because it is going away from neutral. This is of course equilibrium. This is neutral stability, which means it will stay at the disturbed location, which as I said never occurs. Now comes the most important issue, which probably some of you are waiting, but this will take a little time. I am going to draw a long diagram, that's why here. So this is this line. This is, let me put it this way. See here, so this weight is acting. This is my center of gravity G. There is a point here, which is my center of buoyancy B. So this is acting. Okay. Let me call this point to be, you see, another one. People call this to be M. Now here there is this, we will go carefully, because all of us know that intersection of the buoyancy force with the center line, this is the center line, this is the center line of the ship. This is the buoyancy force which intersects the center line at a point, we are calling it M. And we immediately say that if this intersection point stays above G, then we end up getting a restoring moment. In a second scenario, if for example the center of buoyancy went to here, then it would have been like this, and I would have called this to be M. Then we would say that the ship is in unstable equilibrium. So we can say that this intersection point of the buoyancy force along with the center line, if that point stays above G, then the ship is in stable equilibrium. If it is below G, then it is in unstable equilibrium, or it's basically unstable. Okay, so we can call this that in this Gm less than 0 is positive stability. Gm okay. This part actually is well known. I was not aiming at this part. Now my question is that what do you call this point M? You see, here immediately we will be tempted to say that we call it metacenter, but I can tell you that it is not strictly true as on now. Let me say that I have tilted this ship by an angle which is 30 degree. Okay, now tomorrow I tilt it by say 40 degree. Will this point remain same? It will not remain same. Then what is metacenter is a question that we will be now carefully answering. You see, this M, question is M, does it depend on theta? This point, intersection point, we have drawn here. If it depends on theta, then it is obviously not a fixed point. Okay. Now what happens is that when we talk of metacenter, we have to be very careful, and there is a formal definition. You see, the point M is intersection of buoyancy force center line. Okay. Strictly speaking, this point M is a function of theta, because as you have larger and larger angle, we can show it other way around. Now I have to draw this conventional thing. If I tilt it in this way, then I have got this buoyancy coming, it's M. If I tilt it, I will explain this diagram, then it may come to, you see here this diagram. Okay, we are now going to follow a convention where instead of tilting the ship, we will tilt the water line because it is easier to draw. Let us say this is my line. On original water line is this one, WL1. Now I have tilted by an angle, say this dotted line, which has caused my buoyancy to go here, and obviously the buoyancy force acts normal to the dotted line. In fact, it would be convenient if I drew it with another color. Say this line I have tilted, so the buoyancy force acts through this and it intersects at this. So let me call this W1 L W2 L2 and this point to be M, let's say M2 because it's 2 I am using. Now supposing I tilted it further to an angle of to a larger angle, it's something like this, okay. Then obviously it goes to this point, center of buoyancy, and now it goes and this thing, and it intersects another point M3, or I can call this to be M of theta. If I call this to be say theta 2, and theta 2, and this one is M of theta 1 if I call this to be theta 1. You see, this is an important point. In this course we should clarify. The question is that if I have tilted the inclined the ship to some angle theta 1, or I have an intersection point, one intersection point. If I tilted it further to an angle theta 2, I have another intersection point, and as on now I cannot say that the 2 points would be same. I have no basis to say that they are same. They must, we know that they must depend on the angle theta. As I drew it, we will draw one more diagram and a bigger one, because this is a very important way of looking at. I actually brought a scale for that purpose. Draw it in a better way. You just draw a kind of a box type shape. This concept I like to stress on, because this is another fundamental thing that most books do not tell. You see, that is why we are going to spend little time on that. Now I have the initial line. Let me draw it this way. See, I will just draw two lines. What I wanted to say is that, supposing I have line number 1, this is up to just small angle here. Okay, then what happens, that the center of buoyancy will go normal. Let us say it meets here. Just drawing hypothetically this is my intersection through the center of buoyancy of this inclination. Say this is theta 1. This point I will call M theta 1. Okay, I am just calling that. By definition, the intersection point is the metacenter. Now let me take another line like this. Obviously, what would happen, this buoyancy point would have shifted somewhere, and I have to have this thing. Say it or something like, well, it's just exaggerated diagram. This is my, say, nu b. This is my, this point is M theta 2. This is actually, at this point of time, can I say M theta 1 is M theta 2? We cannot say that, because we have no basis to say, you see. Then in that case the question comes, what is metacenter? Okay, if I say the intersection point of that, I cannot prove as on now that the intersection point is independent of the angle, because look at this point B obviously depends on the underwater geometry. This, what is B? B is the centroid of the underwater hull. Okay, see, this green B is the centroid of this green line. This blue one is centroid of this blue line. Obviously, they will depend on the angle of inclination, because blue line is the inclined line by some angle theta. So obviously, this location will, the centroid location will depend on this the amount by which you inclined.
Theta 2 will be below theta 1?
Not, we don't know that. As on now, we don't know that. Normally, it is actually going to be above theta 1. But we don't know that as on now. My point is to prove actually that, really speaking, this definition that we say cannot be adopted for metacenter. So we must be very clear what we mean by the word metacenter. This inclination point, we are seeing this. What then happens is that in initial stability, we would like to know if I tilted it by a very small angle, see if I make theta 1 to be very small, should the vessel stay in that position or not? Our uh, purpose of studying initial stability is to investigate not whether the vessel is stable when I incline it to 30°, but whether it is stable at all in the 0°. That means, will it stay at 0°? What does it mean? Suppose as the wind blows and it has become to 0.01°, slightly shifted, just like as I said, if you want to keep that slightly shifted, it will fall. Okay. Similarly, supposing the ship is shifted by an angle 0.01° or 0.1° or 1° or 2°, a very small amount, we don't know how much. Should it actually become unstable or not? In other words, we would like to find out location of M when theta is very, very small. Where is M for theta very, very small is the question. Now, what is meant by very, very small? What you think is small, he may not think it's small. So, there is no such sort of basic definition. So, we may say now that where is M when theta tends to 0? This is the question. You see, this is the limiting issue that comes. Where is M when theta goes to 0? Now, we will have an interesting situation. So, M is a function of theta. Okay, it depends on theta. Now, if you take limit theta tends to 0, M theta, that means when you make this, now it turns out that this converges to a fixed point. This we will prove later on. When you take theta at the limiting case, theoretically it will turn out that this will actually become a fixed point. In other words, let me put it this way. Supposing I measure theta with respect to theta, some k to m theta, I mean location of m from some reference point. That means there is a ship here, this is k here, this is your m theta. I am investigating m theta with respect to my kill point. As I increase the theta, you will see that it will become actually like this, and it will actually become a straight line and try to approach this thing. You cannot, remember, you cannot reach theta equal to 0. Moment theta is 0, there is no m. See, moment theta is 0, there is no m. But when theta is not 0, but it is small, however small, 0.0001 degrees, then there is an m. So, therefore, it is trying to approach that, but not reaching it. And that is what we call m. That's okay, I think. This is what we call m. Now, this value, this, now if I actually by a color, I extended that to this point, then this value is my m. This is the definition of m. So, the metacenter is defined to be the intersection of the buoyancy force with central line at the limiting case of theta tends to 0. This is very important. What that means, I will write m is the inter see why I insist on that, that in many books they will say at small angles. The word small angle is always a vague now, not very precise scientifically. I mean, what is small is not small enough to, what is small to me is not small enough to you. I say 10 degrees, somebody says 5 degrees, somebody says 2 degrees. What is small? Okay. So, this is again not very precise. On the other hand, we will find out scientifically that small will be a situation where sine theta can be written as theta or tan theta. We have done this before as theta. The limit where you can apply that is small. Strictly speaking, this will be valid only at theta 10 to 0. But then if you do it at theta equal to 0.01 degree, it will be close enough up to say fifth decimal place. If you do 1 degree, up to fourth decimal place, like that. Depending on how much you want to take accuracy, it is basically going to be you know, progressively closer. And what normally we do for ship cases, the scale we talk, people take about 4 to 5 degrees to be small. Then if you take 5 degree, why not 6? The question comes, okay, if 6, somebody says why not 6.5? There is no end to it, but normally we take ballpark figure or whatever around 5 degree, 5-6 degree, because and it is not, there is no cutoff point. It is not that only up to 5 and 6 is bad. See, if you take 5 degree, 5.5 is also good, but not as good as 5. And it progressively it becomes less small. So it's a continuous curve, not a abrupt change of smallness. So when we want to study intact stability at small angle, which is called initial stability, this is called the what initial stability. We normally are talking of stability when the ship is disturbed by a very small amount theta, when theta can be as small as you want. Obviously, when you draw a diagram, you cannot conceive what is meant by theta to be 0.1 degree. A ship 0.1 degree, people laugh at us. What is 0.1 degree, right? So you have to at least have some 3-4 degree, okay? And it turns out 3-4 degree also is very small. Therefore, we normally, when we draw and all, we take 3 to 4 degree. But as I said, strictly this is the situation. This situation may come in some cases when the vessels in offshore structure is just inclined here. Then you know that if you take a small angle 5 degree, it will actually change the water plane. So therefore, strictly speaking, initial stability is concerned with a very small value of theta. We will in fact show now by a formula that M location becomes independent of theta. That also is a confirmation that basically metacenter do not depend on theta as we define. So the concept of metacenter is therefore the concept is valid for theta tends to 0. Why we say that? Because if the theta was not tending to 0, there is no fixed metacenter. It depends on theta. So then we cannot talk. Now if you want to find out shape is stable or not at 30 degree, then you have to have a M for 30 degree or M for 40 degree. You cannot do that. Therefore, we don't use that. We use direct routing lever. We will talk about that. But M become very useful for limiting case of theta tends to 0. So this is a concept that we must bear in mind, this situation of limiting case. Okay. Now we will go actually to try to derive a formula of what happens. How do I locate M? See, obviously the next question is, how do I find out if a ship is initially stable? Obviously, we need to find out metacenter. We need to find out metacenter. We must find out metacenter. So if I can find out metacenter location, metacenter is a point. This is a point. Remember, this is a point. So really, I have to tell I want to know metacenter. Basically means I need to know its coordinate, where M is located with respect to some coordinate system, which means I must measure where is M with respect to some reference point, say kill point or some point. So I must find out this location. Then I can figure out where it is located with respect to center of gravity G, and then I can tell that if M is above G, then the ship is stable. We must remember that G depends on loading. M will find out will depend on geometry. These two are independent things. For a hull at a draft, M is fixed, but for the same hull you can have different loadings. On the other hand, for the if you change the total weight or the orientation, M may change. So it's a question of two different things. This is depending on geometry, so this is actually in hydrostatic parameter, you may say. This arises from buoyancy force. whereas this G arises from the other part, the loading part of it. These two are independent, but the stability depends on interrelation between the two. Where is this located with respect to this? So you see that two different things are there. A ship stable in one loading can be made unstable simply by loading something more, as all of you know that. I mean, all of us know that. So let us try to figure out the formula or the derivation of uh, location of M. I am still calling location of M because we have to find out with respect to what we are trying to find the location. I think I will draw this. I will need to draw slightly smaller because we have to write a lot of equation here. Now, number one is that we are inclining it to some angle. Now, here, see, this is a theta, okay? This is where the problem comes. When we are doing illustration, I cannot draw theta to be very small. I have to draw theta. This looks more like 30 degree, but in reality, it is supposed to be drawn at a very small 2 degree or so. Okay, in reality, it is supposed to be very, very small. So small that this line will pass through this. You see, now this is another point. When theta is very small, our condition is that I must have this immersed volume, this volume and this volume same. Okay. Now consider a case when the situation is that the hull is something like that. So I have this line. Now you see, this is my center line. This is equal to this. If actually I have this line here going to the center line, you can immediately see that this volume is not equal to this volume. Because after all, if you draw a straight line, you see this triangle is this triangle, but this part is less than the triangle by this small amount. This is more than the triangle by this small amount. So if the hull was like this, inclined, it will not pass to the, these two lines will not cross to the center line. Okay. The reason is because, again, if you put a color one, see, our requirement is that this must be same as this, but it is not so, because the shape is changing. But supposing now you take this theta and make theta tends to 0, what would happen? See, in this case, actually the line would have been somewhere here below. See, the line would have been not through center line but somewhere here, because so that the two sides are same. But now when you make theta smaller, it will approach this line, it will come closer to this line. This let me draw this in a bigger way. I want to sort of go slowly and make all the points clear somewhat. This is of course not. Supposing this line, initially when you incline that, say large line, I will do it. It would probably go something like that, so that this area is same. But if I make this smaller, you will find that this will come closer to this. Make it even smaller, it will come closer to this. So this, as I make the inclination smaller, this intersection point will come closer to this center line. And we can prove theoretically that when theta tends to 0, the intersection will indeed be through this. Again, strictly speaking, that is valid only when theta is very small. If not, the ship is wall-sided. If the ship is of course inclined, then so these are the things that we don't tell in the textbook normally, but actually what happens, this is the reality, that if you have an inclination, see, if I draw a flare hull like this, something like this, then it will you can immediately see that it will be through this only when the angle is very small. So now come back to that, I will go to the next slide, that when I drew this line, although it is looking very large, in reality actually it represents a very small angle, so small that the two will intersect through the center line always. So conversely, one can say that only in the case of a theta tending to 0, the two points will intersect at the center line, otherwise not. There are of course formal mathematical proofs, but we won't go to that. So I need to See, I am drawing this straight line only because it is easier with this to draw here, but it would be better to draw a curved line, not a one-sided vessel, because that way it will make the point clearer. Now here we will try to derive the location of meta center. See, this is the center of buoyancy initially, which is center of buoyancy under the waterline WL. But this buoyancy center has basically shifted here to B1. Now again, is it shifted only horizontally? The question comes, or it has also shifted vertically. Remember that here I had a centroid of this location is say G here, and this centroid is G1. It is something like I have cut this piece of cake and added here. That means I have removed this buoyancy force which was there, which is otherwise acting here. I have removed means I have actually added a buoyancy force here, and when I cut this off, I am actually adding a downward buoyancy force because this was giving me upward buoyancy force. So when I removed it, it is equivalent to telling that I am giving a downward force, taking it away and giving it here. That means I am actually producing a moment. Okay. Question is that this centroid and this centroid, is it being shifted only along the horizontal or also along the vertical? Now this diagram of course will again give you a deceptive look that it is actually shifted here and raised vertically. But remember that we are talking of a case when the theta is tending to 0. Again, when you make theta very small, you make it very small, there will be no rise of G to G1. See, this is another point that is deceptive in the diagrams. When I make this angle extremely small, make it 0.1 degree, is something like that, you will find that as if I am simply shifting G from here to here, just horizontally translating, just I am taking here and taking it here. There is no raise. But the diagrams, when you plot, it appears there is a raise. That is because we are incapable of drawing a diagram with theta at 0.1 degree. That is the only reason. Otherwise, we could have shown that. So why the reason that comes in picture is because when theta tends to 0, then B is shifting only along the transverse direction to B1, not vertical direction. There is just a transverse change. Okay, so B shifts to B1 only along waterline, or let's say transverse direction. No vertical shift. The question is that how much is the shift now? Obviously, this can be very easily figured out by using the moments. See, if I take now moments, now through this there is a buoyancy acting of rho g of volume. This multiplied by B to B1 should be equal to, if I have the volume of this slice small v, when small v I will write it down, into G1. Then this is actually volume of the wedge. Note it is volume, not area. This again, this diagram shows an area, but actually you have to take along the length and add the pieces up. Okay, the integration will come afterwards. Let us see what is V then. See, V is equal to half of, this is a triangle. Again, one more thing. It is because when you are making it very small, this becomes a straight line. When I am making theta very small, this line is a straight line. Basically, it can be an arc, but it becomes a straight line because theta is again very small. You are making it again very, very small. Everywhere we have to remember that the entire concept arises only for the case when theta is extremely small. This is very important because when you draw it, and we want to derive from the drawing, you get misled. Why I am saying again, if you do, you will say why it is not a straight line, but remember it is a straight line for our case. So it is half of base into height. Base is actually this much. Say I can call this to be small b, or let me call this to be b here. So half of b by 2. B by 2 is this thing. And how much is this much? This much is b by 2 into tan theta, not b by 2. B by 2 is, see, this is b by 2. This much is b by 2. This is theta. So this is d by 2 tan theta, but tan theta is equal to theta because theta is very small. So it is d by 2 theta, because this part is, remember that when I wrote that, I have assumed already in all this derivation, this as well as this, I have already made the assumption that theta is extremely small. In mathematical terms, theta has tended to 0. It is quite like 0 but not exactly 0. That's what we have said. Otherwise, it will all fall back. So V is this, but it is not fully correct. We should write dx because you have to take the wedge along the length and integrate along the length of the vessel. So this will turn out to be actually 1 by 8 b square theta dx along the length. This is V. Now, what is GG1? GG1, if you see here, G to G1 is actually 2/3 of 2 into 2/3 into b by 2. That is actually 2/3 of b. No, I am talking of the b to be entire thing. So this is b by 2. So this is actually 2/3 of b. Okay. So we have got this 2/3 of b. So we can now very easily figure it out that then rho g v into gg1 gives me rise to integration of 1 by 8 b square theta, there is dx I write, and here I write 2/3 of uh, b over length. This will give me, this goes for b cube 1 by 12 dx, and you see this is theta is there, but theta does not depend on length. Whichever cross section theta is same, so I can take the theta outside here. Okay, I can take the theta outside because theta is whatever angle, it is same for all the this thing. Now this is my rho gv into gg1. This should be equal to rho g into ship volume into bb1. Okay. In fact, no, sorry, this is not rho gv. This is actually I have to multiply rho g here, and in fact I can just delete this part, and I can say that bb1 therefore is actually 1 by volume into 1 by 12 of b cube dx, and I can make the theta here. Say I can make the theta here. Okay. Now this part turns out to be equal to nothing but Ixx by formula. You see this part, because it is actually we should strictly write b to be a function of x bx. That will be better, but I'm just writing actually b is a sectional bit, b is bx. So this part is Ixx. So we can find out that bb1 equal to theta into Ixx by volume. But what is bb1? bb1 is now if you look at the diagram, then we will find out. I will go to this another diagram here. M theta, which will of course becomes bm theta. Again same thing, you see, because theta is always taken very small. So we end up finding that bm theta equal to bb1 equal to theta into Ixx by. Again now one more interesting thing. See, theta is small but not 0. Remember, had it been 0, I could not have cut this out. Okay, but now this is all these tricks we have to play. Theta is very small to 0 but not 0. It can be 0.0000001 but not 0, because if it is 0 then you could not cut from both sides. Okay, so this full thing is valid for a very small angle, therefore I could cut. Many of these mathematical tricks of showing that a is b is based on this idea that a into 0 is b into 0. So fallacy. So 0 cannot be taken out. But in this case, we must remember the entire thing we have done, we have said theta tends to 0, or we have said theta is very small, but we did not say theta equal to 0. This we did not say. You see, if we did say that, then obviously this whole thing will fall. So what happens that for very small angle, we end up finding that Bm equal to Ixx by volume. See, this is, and this Ixx some people call as It. This is what, why people are calling It exactly same way, because it comes in the case of transverse stability. Now you see that Bm is a constant because It does not depend on theta. It is not depending on theta. Volume does not depend on theta. Therefore, m cannot depend on theta in this formula. See, the formula tells me Bm is a constant number. It's a fixed number. But then remember, in the derivation, throughout we have assumed that theta is tending to 0. So you see, only in the case when theta tends to 0, Bm has become T by V, a constant. And this is a point I want to remember, stress. Some people call it BMT in order to distinguish transverse and longitudinal, but the fact that Bm is I by V, which is a very well known formula, everybody knows, all of us know, it emerges from the fact that theta has been taken extremely small but not quite 0. Otherwise, this would not have gone through this. I couldn't have called this sin tan theta as theta. I couldn't have called this straight line, etc., etc. All these things that I have used up at every step strictly is valid only for the case of theta tending to 0. So this is our sort of location. We will end at that. Remember that B is a center of buoyancy, M is a meta center, and it turns out B to M is I by V. So all this thing depends on actually geometric parameter, nothing to do with loading. Center of buoyancy depends on this underwater volume, I depends on the water plane area, volume depends on underwater volume. So entire thing is a hydrostatic or geometric parameter as on now, B to M, B as well as M. We will talk the next lecture about the G part of it. Uh, this one I will conclude saying that we have just proved that Bm is Ixx by V or It by V, and as I said earlier, we call that, but this is really a misnomer. It is really a longitudinal moment of inertia, but we call simply because it is studied in for transverse stability. Thank you.